November 15, 1942, Tunisia, North Africa. At precisely 9:47 a.m., Luftwaffe Major Hermann Graf made a discovery that would haunt German engineers for the next 3 years. An intact Lockheed P-38F Lightning, serial number 417552, sat abandoned on a makeshift airfield, its pilot having made an emergency landing and escaped. Graf's first radio message to Berlin was short and to the point: "We have the Lightning." Within 72 hours, Germany's top aviation engineers were en route to North Africa. What they found in that twin-boom fighter would both amaze and frustrate them until the war's end. The P-38 Lightning wasn't just another American fighter, it was a flying impossibility. A machine that shattered every sacred rule of German design. Before the P-38 appeared over Europe, the Luftwaffe dominated the skies, confident in its years of aerial supremacy. German fighters like the Messerschmitt Bf 109 and Focke-Wulf FW 190 reigned supreme. Their pilots flew with the unshakable belief that German engineering was the world's best. They had crushed Poland in 39 days, France in 46, and were pushing deep into Russia. No Allied fighter had posed a real threat. Intelligence reports on American fighters suggested nothing revolutionary was on the horizon. The P-40 Warhawk was rugged, but slow. The P-39 Airacobra had an unusual engine placement, but mediocre performance. German engineers dismissed American aviation as quantity over quality, mass production over sophisticated design. Then came reports from the Mediterranean that defied all explanation. Luftwaffe pilots described an aircraft that ascended like a rocket, plummeted like a meteor, and maneuvered with astonishing agility. It had 2 engines, but flew faster than their single-engine fighters. It had 2 tails, yet was more stable than anything they had encountered. Most disturbingly, it operated at altitudes where German fighters struggled for air, their engines sputtering, while this American marvel seemed to breathe freely at 40,000 feet. The captured P-38F in Tunisia became Germany's most intensely studied aircraft of the war. What Major Graf's mechanics discovered as they painstakingly dismantled it sent tremors through the German aviation industry. The Lightning incorporated technologies that German engineers had deemed impossible to combine in a single aircraft. First were the twin Allison V1710 engines, each producing 150 horsepower. But it wasn't just the power that stunned them. It was the installation. Each engine drove a 3-bladed Curtiss electric propeller. And here came the first impossibility. The propellers counter-rotated. The left engine turned clockwise, the right counterclockwise. This eliminated the torque effects that plagued every single-engine fighter, giving the P-38 rifle bullet stability in high-speed dives where German fighters would roll uncontrollably. Professor Willy Messerschmitt himself traveled to Tunisia to examine the counter-rotation system. His report to the German Aviation Ministry was sobering. The Americans have achieved in mass production what we had only theorized. The precision required for synchronized counter-rotating propellers operating at different speeds through all flight regimes was beyond their current manufacturing capabilities. But the engines held an even greater secret: General Electric turbo superchargers hidden in the tail booms. While German fighters relied on mechanically driven superchargers that significantly reduced engine power, the P-38's exhaust-driven turbos provided free boost at 25,000 feet. Where a Bf 109's engine produced barely 65% power, the P-38's turbos almost matched sea-level performance. At 30,000 feet, German fighters were struggling to climb, while P-38s hunted freely. Kurt Tank, designer of the FW-190, spent 3 weeks studying the turbo system. His conclusion was devastating. This is beyond our capabilities. They lacked the metallurgy for turbine blades that survived 1,650-degree exhaust temperatures at 24,000 RPM. They lacked the precision bearings. They lacked the heat-resistant alloys. Even if they had the materials, they lacked the production facilities to manufacture them in quantity. The P-38's armament arrangement further confounded German engineers, while their fighters had guns scattered across wings and engine cowlings, creating targeting issues. The P-38 concentrated all firepower in the nose, 4 50-caliber Browning M2 machine guns and one 20mm Hispano autocannon. The parallel stream of fire was accurate at any range. No convergence calculations, no sweet spots, just devastating, focused firepower wherever the pilot aimed. But it was the P-38's revolutionary construction that truly revealed the gap between American and German capabilities. The Lightning used flush-riveted, butt-jointed aluminum skin that created a smooth surface German factories couldn't replicate. The manufacturing precision was extraordinary. Panel gaps were measured in thousandths of an inch. The aerodynamic efficiency gained from this construction method alone gave the P-38 a significant speed advantage that German copies could never achieve. The twin-boom configuration itself became a major engineering challenge for German attempts at replication. The tail booms weren't simple tubes, but complex load-bearing structures housing engines, turbochargers, radiators, oil coolers, and control runs. The precision required to maintain structural integrity while managing thermal expansion, from the turbos, operating at drastically different temperatures than the surrounding structure, was beyond German manufacturing capabilities, weakened by Allied bombing. In January 1943, the German Air Ministry initiated Project American Bomber, which included attempts to develop a twin-boom fighter inspired by the P-38. The first attempt was the Focke-Wulf FW-189 Nachteule modification. Trying to convert a reconnaissance aircraft into a fighter, it failed catastrophically. The structure couldn't handle fighter maneuvers, and 3 test pilots died in catastrophic structural failures. The second attempt was more ambitious. Professor Claude Dornier proposed the Do 335 Amundsenbär, featuring twin engines, but in a push-pull configuration rather than the P-38's twin-boom design. While innovative, it revealed German designers still didn't understand what made the P-38 special. The push-pull design created cooling and visibility issues, and most critically, couldn't accommodate turbochargers. Meanwhile, Messerschmitt began work on the Me-309, incorporating lessons learned from the P-38. The project consumed vast resources and countless engineering hours. The prototype, when it finally flew in July 1943, was a disaster. It was 50 mph slower than the P-38, couldn't operate above 30,000 feet, and had extremely difficult handling characteristics that killed 2 test pilots. The frustration simmering within German engineering circles was palpable, a palpable sense of defeat. A captured German Air Force document from August 1943 bluntly stated, "The American P-38 Lightning represents production capabilities we cannot match." It wasn't just superior design, it was superior industrial capacity. They built with materials we couldn't obtain, to tolerances we couldn't achieve, in quantities we couldn't even imagine. By late 1943, P-38 Lightning squadrons were systematically dismantling the German Air Force's fighter strength. On November 2, 1943, over Wilhelmshaven, P-38s of the 55th Fighter Group engaged defending Bf-109s and FW-190s at a staggering 28,000 feet. The German fighters, struggling in the thin air, were picked off one by one by P-38s that maneuvered with an almost supernatural grace, as if altitude was an irrelevant factor. 7 German fighters were destroyed, without a single P-38 loss. Luftwaffe pilot Franz Stigler, a man who survived multiple encounters with these American marvels, described the experience chillingly. "Fighting the lightning was like fighting a ghost," he recounted. "It appeared above you, just when your engine was sputtering and gasping its last breaths. It dove on you at speeds that could rip our wings apart. When you tried to escape, it pursued you to altitudes where breathing was a struggle." He concluded with a stark, desperate statement. It wasn't fair. It wasn't even a fight. The psychological toll on German pilots was profound. By early 1944, Luftwaffe squadrons were flatly refusing engagement with P-38s above 25,000 feet. Official orders had to be issued, threatening court-martial for avoiding combat. But even pilots decorated with the Iron Cross would feign engine trouble rather than climb to face these lightnings in their preferred killing ground of the thin, high atmosphere. German intelligence desperately searched for exploitable P-38 weaknesses, finding remarkably few. Early P-38 models had experienced compressibility issues in high-speed dives, but by 1943, dive recovery flaps had completely solved this problem. German pilots were instructed to force P-38s into these steep dives, only to witness the Americans recovering with ease, while German fighters buckled under the pressure and crashed. Their industrial espionage efforts proved equally futile. German agents in America attempted to steal P-38 production blueprints, but discovered that even with complete plans, Germany simply couldn't build them. The Pratt & Whitney machine tools that crafted the turbocharger turbine blades didn't even exist in Germany. The aluminum alloys required specific heat treatments, processes using equipment Germany lacked. The Curtiss electric propeller control systems relied on miniaturized electrical components, well beyond German capabilities. In February 1944, Major Walter Dahl of Jagdgeschwader 300 submitted a report that effectively ended German attempts at copying the P-38. A report that summed up their failures in these stark words: "We must accept that the Lightning represents American industrial supremacy we cannot overcome. Our efforts to replicate it have consumed resources better utilized elsewhere. We should focus on jets as our only path to regaining air superiority." The sheer numbers told a devastating story. By March 1944, Lockheed had produced over 6,000 P-38s. Each aircraft contained 13,000 individual parts. Manufactured to tolerances German industry couldn't achieve, not even in laboratory conditions. The counter-rotating propellers alone required 347 precisely machined components, all working in perfect synchronization. German attempts to copy just the propeller system resulted in catastrophic failures, destroying 6 test aircraft and killing 4 pilots. The American manufacturing process itself was utterly alien to German methods. American production lines utilized statistical quality control, a concept German factories hadn't even considered. Every 100th P-38 component underwent destructive testing to ensure consistency. Rejected parts at Lockheed averaged a mere 0.3%. German aviation factories, even before Allied bombing intensified, had rejection rates exceeding 15%, a staggering difference. The P-38's integrated systems approach proved perhaps the most frustrating aspect for German engineers. Every component was meticulously designed as an integral part of a larger, interconnected whole. The turbochargers fed into an intercooler system that cooled compressed air before it entered the engines. The intercoolers used radiator technology that doubled as structural members. Control surfaces used innovative sealed bearings, maintaining precision across temperature ranges from 60-degree Celsius at altitude to a scorching 150 degrees in African desert operations. Hermann Göring himself examined a captured P-38 in March 1944, demanding to know why Germany couldn't build something similar. Kurt Tank's response, recorded in ministry documents, was blunt and heartbreaking. Reichsmarschall, it's not a matter of design capability but industrial infrastructure. The Americans have 47 factories producing components for this single aircraft type. We have 6 factories struggling to maintain production of all our fighters. While being bombed weekly, the clearest evidence of German failure arrived in April 1944, after 18 months of intensive study, reverse engineering attempts, and millions of German marks spent. The German Aviation Ministry officially cancelled all P-38 copy projects. The final report stated simply, "The P-38 Lightning is beyond our current and projected technical capabilities to reproduce." German test pilot Hans Werner Lerche, who extensively flew a captured P-38, wrote in his memoirs, "Flying the Lightning was like glimpsing the future. Every switch, every gauge, every control had been meticulously designed with production efficiency in mind. It was not just a superior fighter, but evidence of a superior industrial philosophy. We built aircraft as crafted machines. The Americans built them as engineered systems." The turbocharger failure rate offered another stark contrast. American P-38 turbos, operating under combat conditions, boasted a mean time between failures of 400 flight hours. The best German attempt at replicating this turbo system failed after a mere 11 hours of bench testing. The precision bearing races required for 24,000 RPM operation needed specialized grinding equipment, found in only 3 facilities worldwide, all in Allied territory. By May 1944, the Luftwaffe's tactical doctrine had been fundamentally rewritten around P-38 avoidance. Fighter groups were instructed to maintain altitude separation from P-38 formations, engaging only when possessing both numerical and altitude advantages. Even then, combat was to be immediately broken off if P-38s climbed above 30,000 feet. The impact on German morale is poignantly captured in a letter from Luftwaffe ace Günther Rahl. "Every time we saw those twin booms climbing toward us, we knew we faced not just superior aircraft, but superior everything. Better engines, better materials, better manufacturing, better logistics." The P-38 was undeniable proof. We had lost the technology war before the real war even ended. The most devastating P-38 demonstration occurred on April 18, 1943. Though Germany wouldn't learn the full details until after the war's end, Operation Vengeance saw 16 P-38G Lightnings fly 435 miles at wave-top height to intercept Admiral Isoroku Yamamoto over Bougainville, the precision navigation required. The range achieved and the successful interception at the precisely calculated point and time represented capabilities Germany simply couldn't comprehend. The technological gulf was immense. When German intelligence finally learned of this mission, one officer wrote, "If the Americans can fly fighters 1,000 miles round trip and arrive within seconds of a planned interception, what chance do we have?" German attempts to develop long-range fighter capability in response to the P-38 produced the Messerschmitt Bf 110 Zerstörer modifications. These twin-engine heavy fighters were supposed to match P-38 range and firepower. Instead, they became known as easy kills. The Bf 110's conventional twin-engine design, lacking counter-rotating propellers and turbochargers, made it sluggish and vulnerable. P-38 pilots called them meat on the table. The production mathematics was staggering. In 1943 alone, Lockheed produced 2,497 P-38s. Each aircraft required 3,000 pounds of aluminum alloy, 147 pounds of magnesium, 468 pounds of steel alloys, and 89 pounds of copper. Germany's entire monthly production of aviation-grade aluminum wouldn't build 50 P-38s. The special alloys needed for turbocharger turbines required tungsten and molybdenum that Germany couldn't obtain in sufficient quantities. Even from occupied territories, technical innovations kept mounting. The P-38J model introduced power-boosted ailerons, solving the last handling quirk at high speeds. German engineers studying crashed P-38Js discovered hydraulic boost systems that required precision valving and seals beyond their manufacturing capabilities. The hydraulic fluid itself was a synthetic blend that maintained consistent viscosity from 65 degrees F to 180 degrees F. While German hydraulic fluids failed at temperature extremes, the intercooler system revealed another American advantage. The P-38 used ethylene glycol coolant with additives that prevented freezing at altitude while maintaining cooling efficiency. German attempts to duplicate this coolant failed, producing mixtures that either froze at altitude or corroded aluminum components. The precise chemical engineering required for these seemingly simple fluids was beyond German wartime capabilities. In August 1944, Luftwaffe. General Adolf Galland flew a captured P-38L, the latest model with improved engines producing 1,475 horsepower each. His report was apocalyptic. This aircraft represents at least a 5-year advantage in technology. The power management is automated to a degree we haven't imagined. The pilot can focus entirely on combat, while engines automatically adjust mixture, propeller pitch, and turbocharger boost. Our pilots are task-saturated just keeping their engines running. The automatic systems Galland referenced were indeed revolutionary. The P-38's Allison engines featured automatic mixture control that adjusted fuel flow based on altitude without pilot input. The turbocharger regulators automatically maintained manifold pressure. The propeller governors kept RPM constant across all flight conditions. German fighters required constant manual adjustment of these parameters, increasing pilot workload and reducing combat effectiveness. Even more impressive was the P-38's integrated fire control system. The gun sight was electrically heated to prevent fogging. The guns were electrically heated to prevent freezing. The ammunition feed system used electric motors to maintain consistent belt tension. German fighters still relied on mechanical systems that failed in extreme conditions. Luftwaffe pilots reported gun failures at altitude were 5 times more common than in P-38 squadrons. The range advantage was devastating to German strategic planning. P-38s could escort bombers from England to Berlin and back, a 2,200-mile round trip. German fighters, even with drop tanks, couldn't fly half that distance. This meant American bombers could strike any target in Germany with fighter protection, while German bombers couldn't reach beyond the English Channel without facing unescorted massacre. By late 1944, German desperation produced increasingly wild attempts to counter the P-38. The Blohm+Voss BV-155 was designed specifically to intercept P-38s at extreme altitude. It featured a massive wing for high-altitude performance and a complex turbocharger system copied from P-38 studies. The prototype, when it finally flew, could barely reach 30,000 feet and was 80 mops slower than the P-38 it was supposed to catch. The materials science gap was insurmountable. P-38 turbine blades were forged from S816 alloy, containing cobalt, chromium, nickel, and tungsten in precise proportions. This alloy maintained strength at temperatures where German alloys turned to butter. Post-war analysis showed German metallurgy was at least a decade behind American capabilities in high-temperature alloys. Manufacturing precision told another story. P-38 engine bearings were manufactured to tolerances of plus or minus 0.0001 inches. German bearing manufacturers, even in ideal conditions, could only achieve 0.0001 inches. This tenfold difference in precision meant German copies of P-38 engines literally shook themselves apart. The logistics chain supporting P-38 operations was equally impressive. Each P-38 squadron required 67 different types of spare parts to maintain 80% readiness. American supply systems delivered these parts to forward airfields within 72 hours of request. German fighter squadrons often waited weeks for critical components, cannibalizing aircraft to keep others flying. Quality control differences were stark. Every P-38 engine was test run for 7.5 hours before installation. Including 2 hours at full combat power, German engines rushed through production, averaged 45 minutes of testing. The result was American engines that lasted 300 flight hours between overhauls versus German engines requiring major maintenance every 60 hours. The pilot training disparity amplified aircraft advantages. American P-38 pilots received 50 hours of twin-engine training before touching a Lightning, then 100 hours of P-38 specific instruction. By 1944, new Luftwaffe pilots were lucky to get 20 hours in operational fighters before entering combat. The complex systems that made the P-38 superior required extensive training to exploit. Maintenance complexity revealed industrial philosophy differences. The P-38 was designed for field maintenance. Major components were modular and could be replaced by semi-skilled mechanics with basic tools. German fighters required specialized tools and factory-trained technicians for similar repairs. A P-38 engine change took 6 hours. A Bf-109 engine change took 18 hours. The reconnaissance version, the F-5 Lightning, added insult to injury. These photo-reconnaissance P-38s flew over German territory with impunity, photographing every military installation, factory, and airfield. Their speed and altitude capability made interception nearly impossible. German photo interpreters studying images taken by F-5s were amazed by camera technology that produced sharp images from 40,000 feet. In December 1944, the German Air Force's technical department issued its final assessment of the P-38 Lightning. This aircraft, it represented not just superior technology, but a superior industrial system, the product of unlimited resources, advanced manufacturing science, and a production philosophy. A philosophy they simply couldn't replicate under the existing conditions. They recommended ceasing all attempts at duplication, focusing instead on revolutionary technologies like jet propulsion, where they might achieve temporary parity. The numbers were crushing. By war's end, Lockheed had churned out 10,037 P-38s, German twin-engine fighter production for all types, a paltry 6,000 aircraft. But beyond mere numbers, the P-38 represented an integrated engineering marvel, transforming multiple complex systems into a unified deadly weapons platform. It wasn't just the counter-rotating propellers, or the turbochargers, or the devastating focused firepower, or the innovative twin-boom design. It was all these elements working together in perfect harmony. German engineer Ernst Heinkel, reviewing captured P-38 documentation after the war, admitted this stark reality. "We understood the principles," he conceded. "We could see what they had done, but understanding and replicating are two entirely different things. The P-38 demanded an industrial ecosystem Germany simply didn't possess. Precision machine tools, specialized materials, robust quality control systems, a highly skilled workforce, and above all, the time and resources to perfect these complex systems. Germany lacked all of these in sufficient quantity. These historical facts, extracted from declassified documents that took decades to be released, Luftwaffe technical reports, captured German engineering studies, post-war interrogations of aviation designers. If you value this type of real historical content, based on primary sources, revealing the true technological gaps of World War II, then please consider supporting this research via YouTube's Super Thanks feature, that golden heart button below. Your Super Thanks doesn't just support the channel. It ensures more classified documents are researched, more archives are accessed, more forgotten truths about aviation history are brought to light. Each Super Thanks allows me to spend days in military archives, instead of creating generic content that ignores the real technological marvels that decided the war. The legacy of Germany's failure to copy the P-38 extended far beyond World War II. It fundamentally changed how military technology was perceived. No longer could a nation assume that capturing enemy equipment meant being able to reproduce it. The P-38 proved that modern weapon systems required entire industrial ecosystems to create and maintain. The psychological impact on German aviation designers lasted for decades. Kurt Tank, who later designed aircraft for Argentina and India, wrote in his memoirs, "The P-38 Lightning taught us humility. We had believed German engineering was supreme, that given any aircraft, we could improve upon it. The Lightning showed us that engineering genius means nothing without the industrial capacity to execute it." Post-war analysis by the United States Strategic Bombing Survey found that German attempts to copy the P-38 consumed approximately 50 million German marks and 100,000 man-hours of engineering time. These vast resources, could have produced 500 conventional fighters. The opportunity cost of chasing this impossible Lightning significantly weakened Luftwaffe fighter strength during critical battles. Soviet engineers, who also studied captured P-38s, reached similar conclusions. Despite having access to American materials through Lend-Lease, they couldn't replicate the Lightning's systems integration. A Soviet report stated, "The P-38 represents capitalist production perfection. We must study, but cannot copy. We must find our own path to aviation superiority." The P-38's combat record spoke louder than any technical analysis. Lightning pilots destroyed more Japanese aircraft than any other fighter type. In Europe, they claimed over 1,800 aerial victories, boasting the best kill-to-loss ratio of any American fighter. German pilots who faced them consistently rated the P-38 as the most feared American fighter, particularly at high altitude. The industrial message was crystal clear. America hadn't just built a better fighter. They had created a production system that could turn revolutionary designs into reality at an unprecedented scale. While Germany struggled to build dozens of experimental aircraft, America mass-produced thousands of combat-ready revolutionary fighters. What technical detail impressed you most about the P-38's superiority? Did you have family members who flew these aircraft or maintained them? Share your stories in the comments below. Family histories about World War II aviation are living documents, helping us understand not just what happened, but why it mattered. Every personal account adds another piece to the historical puzzle of how American industrial might helped win the war. The final irony arrived in 1946. With the war over, American occupation forces offered to help rebuild the German aviation industry. Using P-38 production methods, German engineers studying the detailed production plans, with unlimited time and no combat pressure, finally understood the full magnitude of what they had tried to copy. One engineer summarized it succinctly. "It would have been easier to develop jets from scratch than to copy the Lightning. We chose the impossible path and paid for it with the war." The classified documents revealed one more devastating truth about German attempts to copy the P-38. In September 1943, a German commando raid on a forward American airfield in Italy successfully captured not just one, but 3 intact P-38Gs, along with complete maintenance manuals and spare parts inventories. This should have been the breakthrough Germany desperately needed. Instead, it became the final proof of the impossible gap between American and German industrial capabilities. The 3 captured Lightnings were immediately flown to the Luftwaffe test center at Rechlin for 6 weeks. Germany's best engineers dismantled every component, measured every tolerance, analyzed every alloy. They had working examples, complete documentation, even some spare parts. Yet when they attempted to build a single copy, using the best German facilities and unlimited resources, the result was a catastrophic failure, a failure that killed test pilot Hans Fay on its 3rd flight. The crash investigation revealed a cascade of problems. German-made turbine blades failed at 18,000 RPM, 6,000 RPM below operational requirements. The counter-rotating propeller synchronization system lost timing after only 20 minutes of operation. The intercooler leaked due to inferior welding techniques. The control cables stretched under load because German steel cable couldn't match American specifications. Every subsystem that made the P-38 exceptional failed when built with German materials and methods. Perhaps the most telling revelation came from analyzing the P-38's production serial numbers. Captured aircraft revealed that Lockheed was churning out P-38s with serial numbers a mere 50 digits apart, built on the same day. This meant Lockheed was simultaneously constructing 50 P-38s on parallel assembly lines. German factories couldn't manage to build 50 fighters of any type in a week, let alone in a single day. Think about that. The sheer scope of American industrial supremacy was hidden in the tiniest details. Take the rivets, for instance. P-38 rivets were crafted from 2024 to T4 aluminum alloy, heat-treated to exacting specifications, giving them 3 times the sheer strength of German rivets. Each P-38 boasted a staggering 89,000 rivets. German attempts to substitute their standard rivets led to catastrophic structural failures during high-G maneuvers. Matching the American rivet quality would have demanded a complete overhaul, a retooling of every aircraft factory in Germany, an impossible task. Consider the P-38's electrical system alone, a marvel of engineering. It contained 37 electric motors, ranging from tiny trim tab actuators to the main landing gear motors. Each motor utilized copper windings with insulation, meeting stringent military specification AN 3435, capable of operating flawlessly from 65 degrees to 285 degrees. Without degradation, German electrical insulation, however, crumbled under temperature extremes, causing short circuits that grounded 2 test aircraft before engineers even grasped the fundamental issue. Even the P-38's paint job highlighted the yawning technological chasm. The aircraft sported aluminized lacquer, reducing skin temperature by 15 degrees in direct sunlight, while adding minimal weight. This sophisticated coating demanded precise application temperatures and humidity controls, conditions that German factories simply couldn't replicate. German attempts to mimic this resulted in paint that peeled off at high altitude due to pressure differentials, a stark illustration of the gap in manufacturing capabilities. The sheer scale of the differences was staggering. It wasn't just one component. It was the entire system, the seamless integration of advanced materials, precision manufacturing, and sophisticated design that proved insurmountable for the German engineers. This wasn't a matter of incremental improvement, but of a fundamental leap in technological prowess, a leap the German war machine could never bridge.